This is continuum mechanics. So the first part we discussed in this course, it was continuum mechanics. You need to have continuum mechanics in order to be able to understand the nonlinear finite elements. So this was the first step. And now I'm going to discuss nonlinearity in general for the finite element method. I'm going to refer back to some elements we discussed in the finite element A, and I'm going to show you how these elements may become nonlinear. Now, what I'm going to discuss today is the Newton-Raphson method, basically. And this Newton-Raphson method is the most popular method to solve nonlinear finite element problems. And I'm going to explain the theory behind this method, but what you are going to need this method for is going to be how to implement it in the finite element software. So this is where Dimitrios is going to work with you. All right, so I'm going to talk a little bit more on that later on. But let us start first discussing where the nonlinearity would come from. I would actually say that all the problems you have solved or we solve in engineering are nonlinear problems. It's just that we approximate them as linear problems. Now, in some cases, the linear approximation would not work, and we have to figure out something to deal with these nonlinearities. The materials we studied, so for example, if you look into polymers, they are behaving in a linear way. I don't expect that you have studied a lot of polymers in the past, but the polymers are going to become more and more important in the future, and you will find many applications for them in civil and structural engineering. So this is an important material that behaves completely in a nonlinear way. If you look into the relation between the stress and the strain, you'll see that the relation is anything but linear. And there will be all the nonlinearity we have discussed so far are related to the material behavior. So fractures, failure, this is failure happening in the material, and this is nonlinearity resulting from the material. But there will be also some other types of nonlinearity. For example, if you look into two neighboring buildings and you apply some earthquake loads on that, so this building is going to vibrate in a certain mode, is going to have a certain response. This other one would probably respond in a different mode, or is going to respond in a different way. Now, it is very unlikely that the two buildings are going to respond in phase. So it's not going to happen that this building is going to move in this side, and at the same time, this is going to move in the same side. And then this is going to return, and this is going to return and follow it exactly. This type of behavior is highly unlikely. What is more likely is that these two structures would respond out of phase. So basically, this is going to move in this direction, the other one is going to hit against it. So this behavior is called pounding, and this happens quite a lot in civil engineering if we look into earthquake engineering. And this is a highly nonlinear behavior, because if you design this building itself and you try to analyze the behavior of this building, you can't completely design that, and your building, according to your design, is going to be completely safe. But then there will be a neighboring building that you have not taken into consideration. This neighboring building is going to hit against your own building once an earthquake would happen, and this is going to create a huge impact. This impact is not going to be a linear impact. This is going to be completely nonlinear behavior. And this type of nonlinearity is coming from the geometry. Buckling as well is a nonlinearity resulting from the geometry. And in fact, it's not going to be possible to get a perfect geometry. So this type of issues we have with the geometry would always result into some type of nonlinearity. Now, before I move on, I want to distinguish between two main differences between the nonlinearities we are going to discuss today and nonlinearities in general. What we are going to discuss here is going to be a nonlinear elastic problems. I think probably later on, once you get into the concrete, Dimitrios is going to discuss nonlinear elastoplastic behavior. But what we are going to discuss now is going to be nonlinear elasticity. Now, this is nonlinear because you cannot approximate it with one line. If you try to approximate this with a line, you will be missing quite a lot of the accurate behavior. So you will be severely underestimating the strength that this polymer can take. when you approximate it as a linear behavior. Now, the linear behavior is going to be safe if you pick it on this side, but if you go for this line here, you'll be severely overestimating the behavior at large deformations. So it is up to you which line you pick as a designer. If you know that your stresses are not going to exceed this point, this type of linear behavior is going to be an accurate description. If you want to really get into large deformations, you can probably approximate this in a linear way and lose a lot of the force or a lot of the strength you have in your material. This is going to be up to you as a designer. But there will be one way to treat this nonlinearity and just solve for the exact curve. And this is what we are going to discuss today. Now, this is called elastic nonlinear because when you load and unload, you go back to zero deformations. This is the major difference between nonlinear elastic and nonlinear elastoplastic. Because in the nonlinear elastoplastic, once you exceed the yield point, and you get to this point, for example, and you relieve the stresses, this is not going to come back to zero residual strains. This is going to back to some residual strains. So it's going to fall back, but there'll be some strains remaining inside your material, and this is going to be a significant amount of strain. Now, if you get into this type of behavior, it is not enough to know this curve. It is also important to know the history of this material. So, for example, I'm going to show you some example in plasticity or the elastoplastic behavior, assuming that you have, for example, a concrete beam like this one, and you get into loading this beam. So let us try and draw this behavior. I'm just going to show you roughly how this is going to behave, but it doesn't have, I mean, this is not, obviously this is not exact behavior, but this is just to give you a rough idea on how this would happen. Now, assume that there will be reinforcement in there, and there will be probably reinforcement at the top. So there will be bars at the top and the bottom, and you want to load this. This is the stress, this is the strain. So you start loading this guy, or this beam, is going to yield, is going to start to crack, deformations are going to become big, and then you release the stresses. This is going to come back to zero stresses, but is not coming back to zero strain. There's going to be some residual strain in there. Now, assume that you switch the load, and instead of applying the load downward, you release the load downwards and you apply the loads upward now. Now, this is going to move in a completely opposite direction now. So this is going to move downward, the stress are negative, and the deformation are pushing back in the opposite direction. So the deformation or the strains are going to push back, and they will get into negative strains in there at some point, and it's going to yield in compression. You'll get large strains, and then probably cracks happening at the top. And then you relieve that, it's going to go back, it's not going back to zero strains. There will be still some residual strain, but then in the negative side. Now, let us play this game few circles. So we repeat this several times, you increase it, it yields, it goes back probably at this point this time, and then you load it in the opposite direction, starting from this point. You push it back slightly further, and then you come back, and then you keep moving through this circle several times, probably come back at this point, and then start over, push it, and then probably you fail at this point. Probably it is not complete failure. There is still some strength in this material. And you keep repeating this cycle several times. And by the way, this type of cycles would happen if you have an earthquake. If you have an earthquake, this cyclic loading would happen. And in this case, to understand the material behavior, you really need to know what is the history of this material behavior. Because if you look into this type of curve and you have a specific value for the stress, assuming that this is the stress you have, sigma 1, then for the same value of the stress, you have a range of values for the strain. So this is 1, 2, 3, 4, 5, and 6. So you have 6 values for the strain. So which one is the corresponding one? Of course, it's going to be dependent on the history of your loading. So if you are in the first circle, this is where you get, or this is what you get. If you are in the second circle, this is what you get. If you set the third, the fourth, the fifth. So you have different, basically, values for the strain depending on the location of your load in the time history of your loading. So this is quite a complex behavior, this nonlinear elastoplastic. I mean, it can be simple, just one circle, but it can be a lot more complex. And usually the situation in an earthquake, for example, would be cyclic type of loading, and the failure would happen after several circles. It's not going to happen after the first circle immediately. But if you push this material right to the failure and it fails at this point, then you have just one cycle, and this one cycle can describe pretty much everything. And then you can get an elastoplastic behavior that is similar to what we are going to discuss just now. But if we have an elastic, nonlinear elasticity, then you just, as I said, you just go back all the way to zero strains. This is quite obvious in polymers. For example, if you have a car tire, the car tire would deform quite significantly based on the pressure you have inside it. And then when you release that, it's going to go back to the normal shape. It's going to be zero strains in there. But even with polymers, even with this type of very elastic material, you will see that after several loads, or probably after a year or two, you'll see some cracks starting to show on the tire because of this cyclic loading. Now, with these extra extreme loads for the tire, it's not just that the pressure of the tire would change, but this very flexible material at some point, because of the cycling loading, is going to lead into fracture due to the fatigue you have built up into the history of this material. So in order to understand fatigue, it is very important to understand the cyclic loading as well. So as I said, we are going to discuss a relation between stress strain that is going to be nonlinear. So we are going to discuss nonlinearity due to the material behavior. And this is going to happen only in relation to the stress and the strain. And we are going to strictly limit ourselves to a one-to-one stress-strain relation. So we are not getting into this type of loads where we have multiple strains corresponding to the same stress. We are going to limit our case only to the situation where we have this type of behavior. So it is only one-to-one relation between the stress and the strain up to the failure. Now we are going to again discuss a behavior where we have an elastic material. So as I said, we are not going to get into plastic behavior, but what I'm going to discuss today, so Newton-Raphson method would be valid even if you have an elastoplastic material, and it is also valid if you have nonlinearity coming from the geometry. So you can use it in quite different scenarios, but just to understand the method, it is a lot better to discuss it on a relatively simple scenario. It's not going to be a good idea to discuss it on a complex scenario. All right. And there's one thing I want you to really understand is you are, as an engineer, as a designer, you are the one to decide if your problem is linear or nonlinear. And if you decide that your problem is linear, and this is not going to be a fit approximation, this would mean that your design would face severe challenges, probably failure. So be very careful when you make your decision on working on a nonlinear problem or a linear problem. And in some cases, it may be quite a waste of resources if you get into a nonlinear problem approximation rather than a linear one, because as you probably will see just now, you will see that this is going to lead into a huge computational requirement. I mean, if the CPU time, if the computer time you need to do for solving a problem in a linear mode would be probably 10 minutes, then it can easily get into 10 hours if you are going to solve a nonlinear problem. I mean, just having the same mesh, the same degrees of freedom, but instead of having a linear description of this material, you have a nonlinear one, you would easily move from 10 minutes to 10 hours of CPU time. So you can see that this is not quite an efficient way to solve a problem unless you really need to describe nonlinearity in there. Okay, probably I just mentioned that as well, since I'm discussing nonlinear material properties. So, for example, if you have a fire, the material properties would change, and it is going to be a nonlinear behavior, the type of failure you have eventually in there. So the temperature would keep increasing due to the fire, and this would lead into a change in the material properties as the fire is getting hotter and hotter, or the building is heating up. And then the loads you have in there would stay the same. I mean, the self-weight is not going away. The dead loads you have in your structure are not going to go away. But what you have in there is just a change in the material properties due to the heat. And this will lead into, again, a nonlinear behavior. A serious nonlinearity you will face. I mean, you face a serious nonlinearity in this case. All right. As I said, I'm going to strictly talk about a nonlinear case for an elastic material. If you remember from the finite element method, we have the spring to represent the element, and we have the stiffness relation between this force. So you have a force, you have a stiffness matrix, and you have displacement. It is D1, D2, and then you have K11, K12, K21, K22, and then you have F1 and F2. So these are the forces, and this is the stiffness matrix, and this is what we have in the linear case. So if these entries in there, if these entries are all constant numbers, then this is going to be basically this spring is of a linear behavior, then these numbers in there are all going to be constant numbers. But if they become into functions, I mean, if you think about this, if this is something like E squared added to, or is a function of the displacement, is a function of D1, for example, squared added to some D2, for example. If you get this type of entries in there, then what you have used in the past is not going to work now. So solving a simultaneous set of equations, I mean, you can always solve a simultaneous set of equations. You still have the same number of unknowns as the number of equations, but it's not going to work easily because you have this combination of nonlinear equations. So it's not going to be possible to solve a set of nonlinear equations using substitution. You will have a nightmare in there, especially if you are talking about a large system. So what we are going to do now is to solve a case where these entries basically are not constant. Okay, so this is what I'm going to discuss in there. So I'm not going to discuss this in the context of the finite element yet. I'm just going to introduce the method itself, the Newton-Raphson method, and then we are going to discuss how to implement this in the context of the finite element method. All right, so instead of having a set of equations, let us start from a simple equation. Let us start from an equation like x cubed minus x minus 1, or probably added to x added to 1, which is going to show you the method. I'm just show you the example we are going to solve. This is the first example, so let us restrict ourselves to this simple example. You have a function. I'll probably just write it here in a clear space. You have a function fx is equal to x cubed added to x. And you want to find what is the value of x. Now, if you know what is x, you would immediately find fx, right? If you know x is equal to 1, you put x equal to 1 in there, you will find 1 plus 1 cubed is equal to 2, and the fx is equal to 2. If you have x is equal to 3, you just substitute that in there, you get a value for fx. If x is 1.7, if x is pi, whatever x is, you always get fx. This should be the easy one. Now, how about you know fx? This is known, and you don't know what is the value of x. Now, this is the tricky one, and this is the sort of case we are going to deal with in the nonlinear finite elements problem. Now, let us assume that fx is equal to 5 or 1 or 10. So you need to find the value of x, which will get the value of fx equal to 1. So the way to do this is to try and guess a value of x. Just have a random guess if you want, and then try to improve the random guess. So let us assume that x is equal to 5 or 0 or 1 or whatever, and then we are going to measure the difference between the guess and the actual value of fx. So let us assume that x is going to be probably some number. I'm just going to write it here. And then I'm going to subtract -1. And I'm going to call this function, this new function, the residual function. So the residual function is basically a difference between the value of fx for the guess you have and the actual value of fx. So the value you are looking for is 1, and then you guess a value of fx, or you guess a value of x, you get a value for fx, and the difference between both is going to be the residual function. Now, what you aim for is trying to make Rx equal to 0. So if Rx is equal to 0, if the value of fx, the guessed one, is equal to the actual value of fx, then the residual is going to be equal to 0, and your problem is solved. All right, now this would become easier if we do an example, but I'm going to get into an example later on. Now, this is I'm making the residual function equal to 0 is basically the essence in pretty much all this is the heart of any iteration algorithm. So all iteration algorithms will try to make the residual equal to 0. And there will be different strategies. One of the most efficient strategies is in Newton-Raphson, and I'm going to discuss Newton-Raphson today, but I want you to know that there will be other algorithms, but Newton-Raphson is very popular with the finite element method, and this is why I'm strictly discussing a Newton-Raphson method. So how the Newton-Raphson method would work. So for a Newton-Raphson method, you have a function, fx. This is fx. This is x, and this is fx. And you are interested in finding the x which correspond to some number. So this is p, just a random number, and you want to find actually what is the value of x which correspond to this p here. So in order to do this, you start guessing. So the first guess, you probably assume x is equal to 0, and this is probably the most intuitive guess. So you assume that x is equal to 0, and you evaluate the function at x, and I'm going to explain how the algorithm is going to work, and then I'm going to show you the equations. So you probably don't see it very obvious, the relation between the steps or the steps I'm going to explain in terms of equations and what I'm going to show you in this, but this is basically how the equations are going to work. This is how basically it works, the algorithm. So you guess a value for x, you linearize the function, basically try to find the tangent of the function at this point, you intersect the tangent and this line here. So this is the tangent, this is linearization of the function, and then you intersect this line with the tangent line, and you get another point. So this is another point. You get another point, and you drop this point, you have another value for x. So now your next guess is going to be this intersection point. This intersection point would also intersect with the fx at some point. Again, you linearize at this other point, and you intersect one more time. You drop another point in there. I'm going to call this x0, x1, x2, and you linearize at x2, and you are quite close. I mean, doing this 2 or 3 times will get you into the solution. So this is how Newton-Raphson method works. Now, this is the concept, but I'm going to explain it in terms of equations, or I'm going to show you basically the steps for this algorithm. Okay, so as I said, you may not find it quite intuitive how this approach would be related to the equations. The algorithm itself is a set of equations. But if you think about it, if you try to look behind the equations, you will see this behavior, this algorithm in there. Right? So I'm just going to explain about the algorithm in terms of the steps. So you make an initial guess. Is often the case that you assume 0 as your initial guess. You define first you define a residual function. This is the difference between fx and the value you want to get for fx. This is the residual function. You guess a value of x. You check the residual. If the residual is equal to 0, you have solved the problem. Your guess was spot on. In the majority of the cases, it's not going to be a spot on, and you are going to need some more iterations. So if it is not equal to 0, then you need to go to step number 3. And in the step number 3, you try to find a delta, a value for, you linearize your function. You find the derivative of your function. As I said, you are looking for the tangent. And then you find a new guess based on the relation between the residual and the tangent or the linearization you have done in the previous step. So the new guess is the residual divided by the gradient of the derivative of the residual and subtracted from the initial guess. Okay, so I'm just going to go through the steps in an example, and then hopefully things will become better. Now, obviously, once you get u1 or the new value of fx, x1, you go back to step number 2. You check the residual. If the residual is still not 0, you go through these steps one more time. And you keep repeating this until you get the residual equal to 0, or you get a very small residual. I'm going to solve a first example, and then hopefully things will become better. So we have a function. It is u plus u cubed. This is the function we have. I'll probably just write it in here. I'm just again going to shift down. So we have a function fu is equal to u added to u cubed. So this is the function we have. Now we want to make this function, we want to have fu equal to 1. And in order to do this, we first need to define a residual function. So the residual function Ru is going to be this guy, u plus u cubed, minus this guy, is minus 1. So this is the residual function. We need to find the derivative of the residual function, just the linearization step. So the derivative of Ru, or residual of u, with respect to u, this will be 1. This will be 3u squared, and minus 1, the derivative of that with respect to u is 0. So you get the derivative to be equal to this function there. Now, once you have Ru and the derivative of Ru, you can use that to improve your guess. I'm just going to create a table. As I said, this is the way I do things. And I think the majority of people who would do iterative algorithms would use the same table, but this is completely up to you how you solve your problems. Probably just need to be slightly more neat, I think. Yeah. So I'm going to call the iteration number n, and then I'm going to have a guess for u. I'm just going to call it un, and then I'm going to write the value of Ru, which is what I will check if the function is equal to 0. If Ru is equal to 0, then I would find my solution. And then I would find the R dash u, basically the derivative. And then to improve, I need to add, basically, to find the difference in the value of un. This is n, this is n. So to improve, I need to change the value of my guess by this number. It is minus UR or u, sorry, minus ru divided by the derivative of e. So basically, this is the amount of change I need to make to my initial guess to solve this problem. So I will start by the first iteration. I'm going to call the first iteration iteration number 0. And I'll probably just shift these guys here. I'll have them here so you can see what is it that I'm doing here. I'm going to start by some guess. I can use anything for my guess. 0 sounds like a reasonable guess, so I'm just going to put 0 here. And then I'm going to evaluate RU, R-U, and find the change I need to make in the value of U in order to improve my guess. So the value of RU, I just substitute this 0 in there and here. And the value of RU dash, I just substitute this 0 in here. It's as simple as that. So 0 added to 0 cubed minus 1 is going to be minus 1. If you put 0 in there, 0 squared is 0, multiplied with 3 is still 0, added to 1 is 1. And then minus this guy divided by this guy is minus 1 divided by this one is minus 1 still. I have the negative sign in there, is going to be plus 1. Now I will take this number and add it to my initial guess and get my second round. So at the second round, 0 added to 1 is equal to 1. And then I will use this 1, put it back in here, and solve for a next iteration. So 1 in here, 1 added to 1 cubed is 1, added to 1, so this is 2, minus 1 is again 1. If you come here, 1 added to 3, 1 squared is 4. And then minus 1, so minus 1 divided by 4, this is minus 0.25. Again, I will move it to this one here. I will get the second round. So the second round, or the third round now. So 1 added to 0.2 minus 0.25 is 0.75. And then 0.75, I need to substitute it in here, and in here, and repeat these steps. So 0.75, I probably create an Excel sheet which do the job in a better way. So you have the iteration number, you have the estimation of U, you have the residual of U, and you have the derivative of the residual, and then you have this one. I'm going to use negative sign divided by this one. Yeah, I'm not trying to write a formula, but anyway, so this is meant to be negative. Okay, I'll probably just write it as without using the negative sign. So this is meant to be negative. So the first iteration is 0. The first guess is 0. RU is basically U added to U cubed minus 1. So it is equal to this added to the same to the power of 3 minus 1. So this is this function. And then the derivative is 1 added to 3 . oops. U squared, and then this minus 1 multiplied by this and divided by this. Now, this is going to be basically this one added to this one. So this is my new guess. I just copy these 3 steps. So this is 0.25. This is where I am at the moment. If you repeat, this is the first or this is the second. So if you copy this one down, it's basically going to add this guy to this one. So you have 0.7. You repeat the same thing one more time. You have the residual becoming smaller now. So you are moving from -1 to 1 to 0.17. You start to see the residual becoming smaller. And if you repeat these steps a few times, by the 5th iteration or by the 6th iteration, you get 10 minus 10. Repeat it one more time, you get 0 in real terms. And you see that the residual will be equal to 0. All right. So I want you to think about this and try to solve an example yourself. Use the Newton-Raphson method to solve this equation. So the question here is to find a real root. You only have one real root for this equation. I want you to think about the approach we have discussed just now and to find the one real root for this equation. So think about what is fx. Think what is the value you are looking for fx, what is the residual for that, and how you can minimize this residual, basically following the steps to get into S0. I'm going to give you 5 minutes to think about this, and then I'm going to solve this example myself. So we have the function x cubed minus x1 minus 1, and we want to find the only root. So basically the function we have is fx is equal to x cubed minus x minus 1, and the value of fx we are looking for is the value of fx is equal to 0. So we are trying to make fx is equal to 0. So the residual function is this one minus this one. So the residual function is basically x cubed minus x minus 1 minus 0. I don't need to write it. It's just nothing in there. The derivative of r is going to be 2x squared minus 1. And then the change in the value of my guess, the delta x, is going to be minus rx divided by r dash x. That's it. So I'll just go back to my Excel sheet and change the equations. So this is not going to change. The value of u is not going to change. This, something I have to change. The residual function is x cubed minus x minus 1. I'm just going to type it in there. It's x cubed. This is here to the power 3 minus x and minus 1 is 3x squared minus 1. When I do this equation, that this is 3 times x squared minus 1. And then this column here would also remain the same. So what I need to change is just basically copy these ones. And then I have this set of equations. Now in the question, it is saying to start from an initial guess 1.5. So if you start from 1.5, you would converge quickly. So if you start from 1.5, you converge quite quickly after 4 iterations or 5 iterations, you get 10 to the power minus 13. But if you start from a 0, it is not going to be as quick. So if you start from 0, then you are going to need to do more iterations. I'm just going to show you how many iterations you need to do in order to converge if you start from 0. See, you do have to converge. I think it is copying some. No, there. My mistake. What I did is, instead of, I shouldn't copy the first row, I only need to copy the second and the third row. So if you start with a 0 guess, you are going to need 16 iterations, still not converged. All right, see, once you get to the 20th iteration, you get close to the convergence. Once you get to the 22nd iteration, you would converge. So it does really depend quite a lot on your initial guess in convergence. It is going to converge, but it's going to take more time. And I want you to think about this later on, but this is something we are going to also discuss toward the end of the lecture. Okay, so I want you to keep this in mind. So if you have an initial guess of 1.5, you would converge quite quickly. If you have an initial guess of 1, you would still converge. It's going to be slower. If you start from 6, it is going to converge. If you start from -1, it's going to take more time to converge. So it looks like if you start from a negative number or from 0, it's going to be more time to converge. So I want you to think about this a little bit. Okay, so this is the example. And it would converge within 4 iterations up to 13 digits. So in this example, I'm asking you to find the correct root up to 9 decimal places. And if you do this algorithm with 1.5, you get quite quickly to 9 digits. I mean, more than 9 digits. In this case, I think this is 12 digits or 13 digits. All right. So the algorithm itself is a very powerful tool. And you can use it in so many different things. So I want you to basically, you have learned the tool today, so I want you to think about applications or how to use this tool in different things. So the question is, I want you to use the Newton-Raphson method to find the square root of 10 accurate up to 8 decimal places. And I would suggest you start from 3 as your first guess, because you know that 3 times 3 is 9. 9 is close to 10. So now I want you to think of a method to use Newton-Raphson method to find. So I will leave you to try solving this for 5 or 10 minutes and tell me if you can find it. So you are looking to find, or in this case, you are trying to find the square root of 10 and make your answer accurate to up to 8 decimal places. I mean, this is the algorithm used in a lot of calculators before we have advanced computing facilities. So this was a very successful algorithm to find the square root of a number. So the function you have in this case is x squared, because you are looking for a square root. So the function is x squared, and the value you are looking for is x. And the value of fx you are looking for is 10. So the residual function in this case is going to be 10, is x squared minus 10. And the derivative of the residual is going to be 2x. And the initial guess is 3. I'll just go back to my Excel sheet. So for the first iteration, and the first initial guess is 3. And the value of the residual function is x squared minus 10. So this is this squared minus 10. And the residual is going to be 2x. So it is 2 multiplied with this number. All right, so you just repeat this. Oops. And you should be getting the square root of. This iteration, we'll just erase them. Okay. So it is 3 x squared minus 10. Okay, sorry, I did not update these cells there. Yes, this is updated now. All right, so it actually converged within 4 iterations or 3 iterations. So you have the square root of 10 is 3.16228. So if you look into the iterations, again, the residual function is x squared minus 10. The derivative of that is 2x. And the value you are looking for is 10. And the function itself is x squared. Again, as I said, I mean, this is a tool. You can use it in so many different applications. This is another example. We have I'm using Newton-Raphson method to find the intersection between the two functions. You have two functions. You want to find the intersection between both. And the initial guess is x0 equal to 0.5. So I want you to find the intersection between these two functions. The function you are trying to find, in this case, you are trying to find the intersection between the two functions. So the function you have is fx. You can pick either one of these functions. Fx can be cos x. And then what you are trying to do is to make fx equal to 2x. So it's basically, this is the value you have for fx. You are trying to make it equal to this one. So you can subtract both of them and find the residual between both. This is Rx. The derivative of that is going to be, the derivative of cos x is minus sine x. And this is minus 2. So this is the function, or this is the residual function. This is the derivative of the residual function. And be careful in this case, since you have x and cos x, you need to substitute x in radians. You cannot use degrees for x, all right? So be careful here. So again, you can use the table if you want. I can put it in the Excel sheet, but I think at this point is not much value in using the Excel sheet, but you can try it yourself for the Excel sheet if you want. So this is Rx, this is R-X. You just substitute them in there and you find the change in your function, and within 3 iterations, you'll be able to find pretty much a very accurate answer. So now I'm going to explain the procedure itself on the finite element case. Okay, so I'm going to explain the steps. I want you to see the steps. You are not going to do the steps yourself. Obviously, you are going to use a finite element software. And I think Dimitrios would probably use Adena for the coursework. I think it's going to be up to you to decide on the software you are going to choose. But I think probably Dimitrios is going to explain things on Adena. So you probably can use Adena or something else. But eventually what you are going to do, you are going to use the software. It's not going to be that you do have calculations for this. But these are the steps that are done in the software. Okay, so remember that F is equal to KD. So stiffness multiplied with the displacement is equal to the force. Now, in this case, you don't have a linear relation. So D is not linear anymore. So D is, F is a function of, that is non-linear of the length, of the change in the length. All right. So this is in terms of the strains, if you want. And the function is linear plus cubic. So the relation between the force and the displacement is cubic. And you use the equilibrium equations. You can write the stiffness matrix eventually if you want to. So at the node B, I'm not going to write the equation for node A because at node A you have 0 displacement and you cancel the row and the column. So you are only left with node B and C. So at node B, you have the equilibrium of forces between the force coming from this spring and the force that is coming from this spring. And at node C, you have the force that is coming from the spring opposing the force that is applied at the spring. So this is this one equal to this one. So these are the 2 equations we are going to need to solve. And the displacement in the first spring is UB. The displacement in the second spring is UC minus UB. So the displacement here is B, because this is 0 displacement, and the displacement at this end is the displacement at this spring, or at this end minus the displacement coming from the other end. So this is the displacement you have in the second spring. You find a residual function. So the residual function is basically this one, and this one you have 0, whereas in the second case you have P, so you subtract P. So this is the 2 residual functions you have. And you try to make the residual functions equal to 0. So this is what you are solving with the Newton-Raphson in the nonlinear case. Again, you start from an initial guess. You assume that the displacements are equal to 0. You check the residual. If the residual is different from 0, and it is going to be, in the most general case, going to be different than 0, then you get into step number 3. In step number 3, you linearize. So you linearize, just finding the derivative like we did in the previous case. Find the derivative. Now you have B and you have C, so you need to find the derivative with respect to B and with respect to C. And this is the matrix you have, is called the Jacobian of the residual vectors. So it's basically you combine all of them in one matrix, and then you multiply this Jacobian matrix with the displacement, and you add it to the original displacement. So this is how you get the new displacement. So the inverse of the Jacobian multiplied with the displacement will get you the new displacement. Once you get the new displacement, you again check the residual. If the residual is correct, or if the residual is equal to 0, then this is the end of it. If it is not equal to 0, you find again the Jacobian, you inverse the Jacobian, multiply with the displacement, you get, or multiply with the residual vector, you get the new displacement, and so on. So basically, if you remember, before you had RU divided by R dash U, so the derivative of R, and you divide R by its derivative. In this case, this represents the derivative, and this one here represents the residual vector. So the residual vector multiplied with the inverse of the Jacobian. So this is basically where you get it from. So it is pretty much the same thing, or is a generalization in multiple dimensions.